Welcome back to the channel. Today, we are shifting our focus. We have spent the last few months surviving the crushing silent ice of the Franklin expedition, and we have squeezed ourselves into the suffocating, narrow darkness of the Nutty Putty Cave. In those stories, the enemy was the earth itself, indifferent, cold, and still. But today's story brings us face to face with an enemy that is anything but quiet. We are leaving the silence behind. We are moving from the natural world to the industrial world. Today is a story of roaring engines, screaming metal, and a fire so hot it could melt glass. It is arguably the most terrifying industrial event of the 21st century, yet few people know the true, minute-by-minute psychological toll of the men who were trapped on top of the bomb. This is not just a story about an oil spill. We have all seen the photos of the oil-soaked pelicans. We have all seen the maps of the slicks spreading across the Gulf. But those are the aftermath. The story we are telling today is about the event itself. It is about a machine the size of a skyscraper, floating in the middle of the ocean, that was turned into an inferno by the laws of physics and the hubris of man. It is a story about 126 men and women trapped on a burning island, 40 miles from shore, with nowhere to run. We are building a global community here of people who appreciate dark, atmospheric storytelling. I am always fascinated to see where you are all listening from, whether you're working the night shift in a warehouse, studying late in a library, or just relaxing in the dark at home. So, before we step onto the drill floor, do me a favor, scroll down and leave a comment. Let me know what city or country you are watching from right now. I read every single one. As always, if you appreciate these long-form deep dives, please leave a like on the video. It helps the signal cut through the noise. Now, put on your headphones, turn off the lights, let's go. To April the 20th, 2010. Let's go to the Gulf of Mexico, Chapter 1, The Mud Rain. The ocean at night is a different planet. If you have never been offshore, truly offshore, it is hard to describe the absolute consuming darkness of the open water. 41 miles off the coast of Louisiana, the horizon doesn't exist. The sky and the sea merge into a single infinite void of black. There are no city lights, there are no landmarks. There is only the rhythmic, heaving chest of the Atlantic Ocean and the wind moving over the water. But in the spring of 2010, there was a star in this void. If you were a fisherman standing on the deck of a boat miles away, you would have seen it, a brilliant, glittering city rising out of the waves. It looked like a spaceship that had landed in the water. It was lit by thousands of halogen bulbs, casting a stark, industrial glow against the night. It hummed with the sound of massive diesel engines, a low-frequency vibration that you could feel in your teeth even from a distance. This was the Deepwater Horizon. To call it an oil rig is an insult to the engineering. It was a semi-submersible, mobile, offshore drilling unit, Mode U. It was the size of a football field, 396 feet long and 256 feet wide. It didn't stand on legs that touched the bottom of the ocean. The water here was far too deep for that. Instead, it floated on massive pontoons, submerged 75 feet below the surface to minimize the effect of the waves. It was held in place not by anchors, but by computers. The Deepwater Horizon was a masterpiece of human ingenuity. It possessed a dynamic positioning system. Satellite GPS sensors constantly read the rig's position, and 8 massive thrusters, huge propellers underwater, fired automatically, adjusting thousands of times a second to keep the rig perfectly still over a specific patch of sand on the ocean floor, 5,000 feet below. It was a billion-dollar vessel. It was leased by BP from a company called Transocean, and, in the world of deep-sea drilling, it was the Hercules. It was the rig you sent to do the impossible jobs. It was the rig that had broken the world record for the deepest oil well in history just the year before. But on the night of April the 20th, the Deepwater Horizon was not feeling like a champion. It was feeling like a prisoner. The crew of 126 men and women were exhausted. They were drilling a well known as the Macondo Prospect. And inside the galley, inside the smoking rooms, and on the drill floor, the crew didn't call it Macondo. They called it the well from hell. The project was cursed. They were 43 days behind schedule. They were $60 million over budget. The rock formation they were drilling into, 3.5 miles below the surface, was fighting them every inch of the way. The geology was unstable, fracture-prone, the engineers called it. The gas pressure was dangerously high, and the equipment was being pushed to its breaking point. For weeks, the drillers had been battling kicks. A kick is what happens when the pressure inside the rock is higher than the pressure of the mud in the drill pipe. Gas and oil force their way into the wellbore and shoot up toward the surface. It is the earth trying to vomit out the intruder. But the crew of the Deepwater Horizon was good. They were the best in the business. They had managed the kicks. They had wrestled the well into submission. By 9:01 p.m. on that Tuesday night, the mood on the rig was actually lightening. They were done. The drilling was finished. They had reached the target depth of 18,360 feet. They had cemented the well shut. They were in the temporary abandonment phase, preparing to cap the well, disconnect the rig, and move on to the next job. The heavy lifting was supposed to be over. Up on the bridge, the captain was monitoring the weather. Down in the galley, the night shift was eating dinner. In the movie theatre room, men were watching action films, unwinding after a 12-hour shift. But down on the drill floor, the heart of the machine, something strange was happening. The drill floor is a loud, dangerous and dirty place. It is a mesh of heavy steel suspended over the moon pool, the open hole in the center of the ship where the drill pipe descends into the ocean. It smells of grease, diesel and drilling mud. Drilling mud is a vital component of the operation. It's a thick synthetic fluid, heavy and viscous, that is pumped down the pipe to lubricate the drill bit and, crucially, to provide weight. It is the weight of this mud that acts as a cap, holding back the immense pressure of the oil and gas deep in the earth. At 9:40 p.m., the floor crew, roughnecks, drillers and tool pushers, were busy. They were bleeding off pressure from the riser pipe. It was a routine procedure. Then they heard a sound. It started as a hiss, like a steam valve left open. Then it became a rumble. The deck beneath their boots began to vibrate. Not the rhythmic vibration of the thrusters, but something erratic, something violent. Suddenly, from the top of the derrick, the high metal tower that rises hundreds of feet above the deck, it started to rain. But it wasn't water. Thick, black, oily sludge began to splatter onto the hard hats of the men working on the floor. It hit the steel deck with a heavy, wet slap. "What is that?" one of the roustabouts yelled over the noise. They looked up into the floodlights. The drilling mud wasn't being pumped down anymore. It was being shot up. The pressure from the bottom of the well, 3 miles down, had found a weakness. It had punched through the cement barriers that were supposed to seal it. It had raced up the riser pipe, expanding as it came, pushing a column of heavy mud ahead of it, like a bullet in a gun barrel. The mud hit the top of the derrick with such force that it shot 240 feet into the air. It was a geyser of filth. For a few seconds, the men on the floor just stared. It was a phenomenon so rare, so catastrophic, that their brains struggled to process it. Mud isn't supposed to rain. The system is a closed loop. If mud is raining, it means the loop is broken. It means the monster is out of the cage. "Well control situation," someone screamed. The drill shack, the control room with windows overlooking the floor, lit up with alarms. The mud rain was the warning shot. It was the earth clearing its throat, because drilling mud is heavy. It moves relatively slowly. But what was pushing the mud was gas, methane, highly pressurized, volatile, and invisible. As the men scrambled to figure out what was happening, slipping on the slick black coating that now covered the deck, the mud rain stopped as abruptly as it had started. Silence returned for a heartbeat, but it was a lying silence. The mud was gone because the gas had overtaken it. The riser pipe was now filled not with heavy fluid, but with explosive vapor moving at supersonic speeds. The mud rain was the visual cue that the Deepwater Horizon had just lost the war. The physics had tipped. The hydrostatic pressure had failed. The men on the drill floor didn't know it yet. They couldn't know it, but they were standing on top of a volcano that had just erupted. The lava wasn't molten rock, it was hydrocarbons, and it was about to meet the ignition sources of the rig's engine room. The rain was over, the fire was coming. Chapter 2. The City at Sea. To understand the tragedy of the Deepwater Horizon, you first have to understand the sheer magnitude of the thing that was lost. In the popular imagination, an oil rig is often pictured as a rusty stationary platform on metal legs, sitting in shallow water near the coast, pumping oil like a rhythmic, nodding grasshopper. The Deepwater Horizon was not that. The Deepwater Horizon was to the oil industry what the Apollo rockets were to space exploration. It was the pinnacle of human engineering. It was a semi-submersible, mobile offshore drilling unit, MODU, a designation that sounds clinical but describes a vessel of almost science-fictional capability. Built in Ulsan, South Korea, by Hyundai Heavy Industries in 2001, it cost $560 million to construct. Adjusted for inflation and the specific upgrades added over the years, it was essentially a billion-dollar asset floating in the Gulf. It was massive. The deck of the rig was 396 feet long and 256 feet wide, larger than an American football field. From the keel to the top of the drilling derrick, it stood 32 stories tall. If you placed the Deepwater Horizon in the middle of a downtown city, it would dominate the skyline. It weighed 33,000 tons. But the true marvel wasn't its size, it was its buoyancy. Unlike traditional platforms that are pinned to the ocean floor, the Deepwater Horizon was designed to float in water so deep that anchoring it with chains was physically impossible. It sat on two massive underwater pontoons, huge, submarine-like structures that provided the lift. These pontoons were submerged 75 feet below the surface, placing them below the turbulent action of the waves. This design allowed the rig to remain eerily stable, even in rough seas. While a supply ship next to it might be pitching and rolling violently in a storm, the Deepwater Horizon would barely move. It was a fortress of stability in a chaotic ocean, and it was kept there by a brain. The rig utilized a technology called Dynamic Positioning Class 3, DP3. This system was the pride of Transocean, the company that owned the rig. It consisted of satellite GPS sensors that constantly triangulated the rig's exact position on the surface of the Earth. These sensors fed data into a central computer, which controlled 8 massive thrusters, giant rotatable propellers hanging off the bottom of the pontoons. These thrusters were not small outboard motors. Each one was the size of a small house. Each one could generate thousands of horsepower. The computer would detect if the wind or the current pushed the rig even a few inches off target. Instantly, it would fire the appropriate thrusters to push back. It made thousands of micro-corrections every minute. It allowed this 33,000-ton beast to hover over a drill hole on the ocean floor, 5,000 feet down, with the precision of a surgeon's scalpel. It could hold its position within a radius of a few feet, even in a hurricane. This technology gave the crew a sense of invincibility. They weren't just sailors, they were the masters of the environment. They had tamed the ocean with math and steel, but the Deepwater Horizon wasn't just a machine, it was a home. For the 126 people on board, the rig was a self-contained city. It had everything they needed to survive and stay sane during their 21-day shifts. The hotel section of the rig was designed for comfort. The cabins were small but clean, usually shared by 2 workers. There was a galley that served 4 meals a day, high-calorie, high-quality food to fuel the exhausting physical labor. Steak nights, fresh seafood, an ice cream bar that was open 24/7. In the isolated world of offshore drilling, food is morale, and the Deepwater Horizon ate well. There was a movie theater with leather recliner seats. There was a gym with treadmills overlooking the endless blue water. There was a recreation room with pool tables and ping-pong tables. The rig had a hierarchy, a social structure as rigid as a military vessel. At the top were the company men. These were the representatives from BP, British Petroleum. They were the clients. They rented the rig from Transocean at a cost of roughly $500,000 per day to drill the hole. They called the shots on what to do. Donald Vidrine and Robert Calusa were the ranking BP men on board that night. Their job was to ensure the well was drilled quickly and cheaply. Below them were the Transocean managers. Jimmy Harrell was the Offshore Installation Manager, OIM. He was the captain of the ship. His loyalty was to the rig and the crew. His job was to ensure how it was done, and that it was done safely. And then there was the crew, the roughnecks, the roustabouts, the crane operators, the mudloggers, the galley staff. They were a mix of hardened oil veterans and young men looking for a big paycheck. They worked 12-hour shifts, 12 on, 12 off, for 3 weeks straight. Then they would fly a helicopter back to the mainland for 3 weeks of rest. It was a lucrative life. A young man with no college degree could make 6 figures working on the Deepwater Horizon. But the cost was isolation. You have to understand where they were. The Macondo Prospect is located in Mississippi Canyon, Block 252. It is 41 miles off the coast of Louisiana. That might not sound like far, but on the water, 41 miles is the other side of the moon. When you stood on the helipad of the Deepwater Horizon and looked north, you couldn't see America. You couldn't see land. You saw nothing but the curvature of the earth and the slate-grey water. At night, the isolation was absolute. The rig was a bubble of light in a universe of darkness. If something went wrong, you couldn't just call 911. You couldn't run to the neighbors. The nearest hospital was an hour away by helicopter, and that was assuming the weather was good enough to fly. If the weather was bad, you were on your own. This isolation fostered a tight-knit culture. The crew knew each other's families. They knew who had a new baby, who was going through a divorce, who was saving up for a new truck. They trusted each other with their lives, because the work they did was inherently lethal. The drill floor was the dangerous heart of the city. It was a place of swinging iron, high-pressure lines, and slippery surfaces. The roughnecks who worked there were the infantry. They were strong, skilled, and incredibly tough. They handled the drill pipe, 30-foot sections of heavy steel, connecting them one by one to create the string that reached down to the ocean floor. And what a reach it was. The environment they were drilling into was alien. First, there was the water, 5,000 feet of it. That is almost a mile of vertical ocean. At that depth, the water temperature is near freezing. The pressure is crushing. Light does not exist. The only things that live down there are strange, bioluminescent creatures and blind fish. Then, there was the rock. Once the drill bit hit the sea floor, it had to chew through another 13,000 feet of earth. This wasn't solid granite. It was a Miocene formation, a chaotic layer cake of sandstone, shale, and salt. Salt is a driller's nightmare. It moves. It creeps. It behaves more like a slow-moving liquid than a solid rock. And trapped beneath these shifting salt layers were pockets of ancient life, plankton and algae that had died millions of years ago, been cooked by the Earth's heat, and transformed into hydrocarbons, oil and gas. But at 18,000 feet, these hydrocarbons are not passive. They are under unimaginable pressure. The reservoir pressure at Macondo was estimated to be over 11,000 pounds per square inch, psi. To put that in perspective, the pressure in a car tire is about 35 psi. The pressure in a scuba tank is 3,000 psi. 11,000 psi is enough to cut steel. It is enough to crush a submarine. It is a force that wants desperately to escape. It wants to shoot up the path of least resistance, the drill pipe, and equalize with the surface pressure. The only thing stopping it was the Deepwater Horizon. Specifically, the mud. The entire operation relied on a delicate hydrostatic balance. The crew pumped drilling mud, that heavy synthetic fluid, down the pipe. The weight of the column of mud pushing down had to be greater than the pressure of the oil pushing up. It was an arm wrestling match with the planet. As long as the mud was heavy enough, the planet lost. The oil stayed in the ground. But on April 20th, the Deepwater Horizon was preparing to let go of the arm. They were finishing the well. The plan was to plug the hole with cement, disconnect the rig, and sail away. leaving the well capped for a production platform to come later and extract the oil. To do this, they had to remove the heavy mud and replace it with seawater. Seawater is light. It provides very little downward pressure. This meant the cement plug had to hold. It was the only barrier left. There was a palpable sense of get it done on the rig that week. The delays had been costly. Every day the rig sat there cost BP money. The executives were frustrated. The schedule was red. This pressure filtered down from the boardroom to the rig floor. There was a subtle, unspoken push to cut corners, to skip unnecessary tests, to interpret data in the most favorable light possible. It is a phenomenon known as normalization of deviance. When you take a risk and nothing bad happens, you assume the risk was safe. You do it again. You push the line a little further. Over time, the unacceptable becomes the standard. The Deepwater Horizon had been pushing the line for weeks. They had used fewer centralizers, devices to keep the pipe centered, than recommended. They had skipped a cement bond log, a test to check the quality of the cement. They were relying on a negative pressure test that had given confusing results, but looking at the rig on the surface, you would never know the danger. It looked majestic. It looked secure. At 9:30 p.m. the lights of the rig were reflecting off the calm water of the Gulf. The thrusters were humming, keeping the beast perfectly still. The crew in the galley were finishing their ice cream. The men on the drill floor were laughing, joking about what they would do when they got home in a few days. They were living in a city at sea, protected by the best technology money could buy. They felt safe. They didn't realize that 5,000 feet below their boots, the cement had already failed. They didn't realize that the arm wrestling match was over and the Earth had won. The gas was already in the pipe. It was silent, it was invisible, and it was rising. The city at sea was about to become a battlefield. Chapter 3. The Schedule from Hell. In the world of deep-sea drilling, time is not measured in hours or minutes. It is measured in dollars. To operate a rig like the Deepwater Horizon costs roughly $1 million per day. That includes the leasing fee to Transocean, about $500,000. The cost of the support vessels, the helicopters, the fuel, the mud, the cement, and the salaries of the 100+ men on board. Every time the sun rose over the Gulf of Mexico, BP was spending a fortune. By April 2010, the Macondo Prospect wasn't just costing money, it was hemorrhaging it. The project was originally scheduled to take 51 days. By the time the sun set on April 20th, they were on day 74. They were 43 days behind schedule. The budget, originally set at $96 million, had ballooned to over $140 million. Every morning, the company men, the BP site leaders on the rig, would wake up, look at the reports, and see red ink. Every phone call from the executives in Houston was about the timeline. When are you finishing? Why are we stopped? Get it done. This financial pressure created an atmosphere on the rig that was thick with tension. It wasn't a panicked atmosphere. These were professionals. It was a subtle, grinding pressure. It was the kind of pressure that makes smart people make stupid decisions. It was the kind of pressure that turns safety from a philosophy into a checklist item that you just want to get through. But the delays weren't just bad luck. They were a warning. The Macondo well was fighting back. From the very beginning, the geology of the Macondo Prospect had been hostile. The crew didn't call it Macondo. In the smoking rooms and the galley, they had a different name for it, the Nightmare Well. The problems began in October 2009 with a different rig, the Marianas. That rig had started drilling the well, but had been forced to abandon it when a hurricane swept through the Gulf and damaged the vessel. The Deepwater Horizon was brought in to finish the job, inheriting a hole that was already cursed. As they drilled deeper, the rock formation became increasingly unstable. They hit a kick, an influx of gas, in early March. The drill pipe got stuck in the hole. The formation was so fractured and the pressure was so high that the rock literally grabbed the pipe and wouldn't let go. They had to use explosives to sever the pipe, back up, and drill a bypass, a new hole around the stuck equipment. That alone cost them weeks and millions of dollars. Then there was the lost circulation. Drilling mud is supposed to go down the pipe, cool the bit, and come back up the sides, bringing rock cuttings with it. It's a loop. But the rock at Macondo was so rotten and fragile that it would sometimes crack under the weight of the mud. The mud would just disappear into the cracks. Thousands of barrels of expensive fluid, vanishing into the earth. When you lose circulation, you lose your primary defense against a blowout. You are flying blind. To fix this, the BP engineers made a critical decision. They decided to use a different kind of chemical spacer and to be very careful with the pressure they applied. They were walking a tightrope. If they used mud that was too heavy, they would crack the rock and lose circulation. If they used mud that was too light, the gas would shoot up and kill them. The margin for error was razor thin. By mid-April, the crew was exhausted. They had been fighting this well for months. The equipment was battered. The annular preventer, a giant rubber donut in the blowout preventer designed to seal the well, had been damaged weeks earlier. A chunk of rubber had come up in the drilling. Fluid. Did they stop to fix it? No. To pull the BOP stack up from the sea floor would take days. It would cost millions. They kept going. They assumed the other safeguards would work. This is the normalization of deviance. It is the most dangerous psychological trap in high-stakes industries. It's the idea that if you break a rule and nothing bad happens, the rule must not have been important. On the morning of April 20th, this pressure to finish culminated in a visit from the VIPs. 4 BP executives flew out to the rig for a management visibility tour. They were there to celebrate. The well was essentially done. The rig had gone 7 years without a lost time incident, a major injury. They were there to hand out awards. The irony is staggering. At the exact moment the executives were in the conference room congratulating the crew on their safety record, the engineers were making the final fatal decisions that would doom them all. The conflict centered on the centralizers. When you put the final steel casing, the pipe, into the hole, you need it to hang right in the center. If it leans against the side of the rock, the cement won't flow evenly around it. You'll get a channel, a gap in the cement where gas can sneak through. To prevent this, you use metal clips called centralizers. The Halliburton contractor, the company in charge of the cement, recommended using 21 centralizers. Their computer models showed that anything less would result in a severe gas flow problem, but BP only had 6 centralizers on the rig. To get more would take another 10 hours. It would require flying them out by helicopter or waiting for a boat. The BP manager on shore, John Guide, made the call. In an email that would later be read in court, he wrote, "It will take 10 hours to install them. I do not like this. Who cares? It's done. End of story. We'll probably be fine." They went with 6. They knowingly ignored the recommendation of the experts to save 10 hours on a project that was already 43 days late. They ran the casing. They pumped the cement. And then they argued about the bond log. A cement bond log, CBL, is a test where you lower a sonic tool down the pipe to listen to the cement. It tells you if the cement has set properly. It costs about $128,000 and takes roughly 12 hours. Given the trouble they had with the centralizers, and given the nightmare nature of the well, a CBL was essential. It was the only way to be sure the well was sealed. BP decided to skip it. They sent the Schlumberger team, the contractors who performed the test, home on the early helicopter. They reasoned that the cement job had gone smoothly enough, and that the test was a waste of time and money. By the afternoon of April the 20th, the timeline had won. Every decision that could have been made to prioritize safety, waiting for centralizers, running the bond log, circulating the mud longer to check for gas, was discarded in favor of speed. The crew was told to prepare for the negative pressure test. This was the final exam. If the well passed this test, they could pull up the anchor and leave. The mood in the drill shack was focused but optimistic. They could see the finish line. The BP company men, Vidrine and Kaluza, were pushing the Transocean drillers to get on with it. But the well wasn't done with them. Down in the dark, 18,000 feet below, the cement was failing. The 6 centralizers hadn't been enough. The casing was sitting against the rock. The cement had channeled. While the executives were eating lunch and praising the safety culture, tiny bubbles of methane gas were already finding their way through the flaws in the barrier. The schedule from hell had forced the crew to construct a prison for the oil that had no bars. The machine was huge, the technology was advanced, but the decision-making was primitive. It was driven by the oldest motivation in human history, greed. The sun began to set on the horizon. The night crew came on shift. They walked onto a rig that was essentially a loaded weapon with the safety catch filed off. And the trigger was about to be pulled. Chapter 4, The Phantom Seal. If you strip away the billion-dollar technology, the satellite positioning systems, and the complex geology, the safety of an oil well comes down to one primitive ancient material, cement. It is the final line of defense. When you drill a hole into a pressurized reservoir of oil and gas, you are essentially opening a door that the earth wants desperately to kick down. The drilling mud keeps the door closed while you are working, but you can't leave the mud there forever. Eventually, you have to replace the liquid mud with something solid. You have to lock the door. That lock is the cement. The process is called cementing the casing. It sounds simple, like pouring a sidewalk, but at 18,000 feet, it is a high-wire act of chemistry and physics. You pump wet cement down the center of the hollow steel pipe. It goes all the way to the bottom, flows out the end, and then is pushed up the outside of the pipe, filling the narrow gap between the steel and the raw rock. This gap is called the annulus. When the cement hardens, it turns that gap into a solid stone wall. It bonds the steel to the rock. It stops the gas from moving up. It seals the reservoir. Once the cement is set, the well is dead. It is safe. You can disconnect the rig and sail away. But at the Macondo well, the cement wasn't a lock. It was a sieve. To understand why, we have to go back to the nightmare geology. Remember the fracture gradient. The rock at the bottom of the Macondo well was fragile. It was weak. If you pumped standard, heavy cement into that hole, the sheer weight of the column would crush the rock. The rock would crack. The cement would vanish into the formation, and you would be left with no seal at all. So BP and their contractor Halliburton had a problem. They needed a cement that was strong enough to hold back the gas, but light enough not to break the rock. The solution they chose was nitrogen foam cement. This is exactly what it sounds like. They inject nitrogen gas into the wet cement slurry as it is being pumped down. The gas creates millions of tiny bubbles, frothing the cement like a milkshake. This expands the volume and drastically lowers the weight. It allows you to create a column of cement that is light enough to sit gently against the fragile rock. But foam cement is chemically temperamental. It is unstable. Imagine a bottle of soda. If you keep the cap on tight, the gas stays dissolved in the liquid. But if you shake it or change the pressure, the gas wants to break out. It wants to separate. If the nitrogen bubbles in the cement become too big, or if they connect with each other, they don't just make the cement light, they make it permeable. The bubbles link up to form a chain, a microscopic tunnel through the hardening stone. Instead of a solid barrier, you get a sponge. And at Macondo, the chemistry was screaming a warning. In the days leading up to the disaster, Halliburton conducted a series of lab tests on the specific foam recipe they planned to use. These tests were done on shore, in a safe, controlled environment. The results were terrifying. In at least 3 separate tests, the cement slurry failed. It was unstable. The nitrogen wouldn't stay in suspension. The foam collapsed. In one test, the mixture took an incredibly long time to harden. In another, it settled into a layer of heavy solids and a layer of free gas. If your cement turns into gas, it isn't a seal, it's a highway. Jesse Galliano, the Halliburton cementing engineer, sent an email to BP with the results. He warned about the risk of severe gas flow. He recommended using more centralizers, the devices BP had already decided to skip, to help the cement flow evenly. But the pressure of the schedule from hell was the overriding force. To redesign the cement slurry would take time. To wait for new chemicals would take days. to run more tests would delay the departure of the rig. BP decided to proceed with the foam cement. They assumed that the pressure down in the well would be high enough to keep the nitrogen in solution until the cement set. They gambled on the physics. On the evening of April 19th, the day before the explosion, the cement job began. It was a massive operation. The pumps on the Deepwater Horizon roared to life. They pushed 51 barrels of the foamed slurry down the throat of the well. The crew watched the monitors. They watched the flow rates. Everything looked normal on the surface. The pumps pushed the cement down, the pressure held, and the job was declared finished. But down in the dark, the phantom seal was forming. Because they had used only 6 centralizers, the pipe wasn't centered in the hole. It was leaning against the side of the rock. As the foamed cement flowed up the annulus, it took the path of least resistance. It flowed easily on the wide side of the gap, but it struggled to fill the narrow side where the pipe touched the rock. This created a channel, a long, thin strip of wet mud and uncured cement running up the side of the wellbore. And then the chemistry failed. As the cement sat there, waiting to harden, the heat of the earth, over 200 degrees Fahrenheit, and the complex interaction of the chemicals caused the nitrogen foam to destabilize. The bubbles broke, the gas separated. The barrier that was supposed to be a solid wall of stone was now riddled with microscopic fractures and voids. It was a honeycomb. But up on the rig, they couldn't see this. Cement is an invisible process. You pump it down and you trust it. You can't look at it. The only way to know if it worked is to run that cement bond log, the sonic test that BP had sent the crew home to avoid paying for. So at 12:00 p.m. on April the 20th, the crew of the Deepwater Horizon believed they were safe. They believed the door was locked. They believed the monster was caged. In reality, the door was just resting on the latch. The phantom seal is the most insidious part of this tragedy. It created a false reality. If the cement had failed obviously, if they had seen fluid leaking immediately, they would have stopped. They would have kept the heavy mud in the well. They would have spent another week fixing it. It would have cost $5 million, but everyone would have gone home alive. Instead, the cement failed silently. It held just enough pressure to fool the initial checks, but it was too weak to withstand the full force of the reservoir once the heavy mud was removed. It was a time bomb made of grey sludge. The crew began the next phase of the operation, temporary abandonment. This involved setting a mechanical plug inside the pipe as a backup to the cement. But here, the timeline gets murky. The procedure was complicated. They were setting a lockdown sleeve. They were displacing mud. They were running tests. The crucial thing to understand is that all of their subsequent actions, removing the mud, unloading the seawater, were based on the foundational lie that the cement was solid. They were taking the weight off the well because they thought the bottom was sealed. Imagine a man standing on a trap door. He thinks the bolt is slid shut, so he takes off his safety harness. He relaxes, he smiles, but the bolt isn't shut. It's made of paper. As the afternoon of April 20th wore on, the hydrostatic pressure inside the well began to drop as they pumped the heavy mud out and replaced it with seawater. The balance was shifting. Deep in the reservoir, the gas sensed the weakness. The 11,000 psi of pressure pushed against the nitrogen foam. It found the channels. It found the connected bubbles. Slowly, silently, the hydrocarbons began to migrate. It wasn't a roar yet. It was a whisper, sayuaita, trickle of gas moving through the phantom seal, entering the casing, and beginning the long, buoyant climb toward the surface. The negative pressure test, the test that was supposed to catch this failure, was coming up next. It was the last chance to detect the ghost in the machine. But the phantom seal had already done its work. It had lulled the rig into a state of complacency. It had turned the Deepwater Horizon from a drilling vessel into a target. The cement, the material that has been used since the days of the Romans to build empires, had been corrupted by haste and hubris. Instead of a foundation, it became a tombstone. Chapter 5. The Test That Lied. In the timeline of every disaster, there is a specific moment where the event stops being a probability and starts being an inevitability. It is the point of no return. For the Titanic, it was the moment the lookout spotted the iceberg too late to turn. For the Challenger, it was the decision to launch in freezing temperatures. For the Deepwater Horizon, that moment happened between 5 p.m. and 8 p.m. on the evening of April the 20th. It happened in the driller's shack. The driller's shack is the nerve center of the rig floor. It is a small glass-enclosed room where the driller sits in a specialized chair, the cyber chair, surrounded by screens, joysticks, and gauges. From here, he controls the massive machinery. He can see the pressure in the well, the torque on the bit, and the flow of the mud. At 5 p.m., the crew was preparing for the most critical safety check of the entire operation, the negative pressure test. To understand the horror of what happened next, you have to understand the simplicity of this test. The concept is basic physics. To prove that the cement at the bottom of the well, the phantom seal, is holding, you have to simulate the condition of abandonment. You have to remove the heavy pressure from inside the pipe and see if the well flows. Imagine a tire. To check if a patch is holding, you might inflate it and put it underwater to look for bubbles. The negative pressure test is the reverse. You reduce the pressure inside the pipe to 0 or close to it, so that the pressure inside the rock is higher than the pressure inside the pipe. If the cement is solid, nothing happens. The pressure gauge should read 0 and stay at 0. But if the cement is leaking, if there is a channel, the high pressure gas from the rock will push through. It will enter the pipe, and the pressure gauge on the surface will rise. It is a binary test. Pass or fail. 0 or not 0. Life or death. The test began, shortly after 5 p.m. The Transocean drill crew, led by the driller Dewey Rivette, closed the blowout preventer, BOP, on the seafloor to isolate the well. They then opened a valve to bleed the pressure in the drill pipe down to 0. They watched the screens. The pressure dropped. It hit 0. For a moment it looked good, but then the physics of the phantom seal kicked in. The pressure started to creep up. It didn't skyrocket, but it didn't stay dead. It climbed. It rose to 1/400 psi. This is a massive red flag. 400 pounds per square inch of pressure appearing in a pipe that is supposed to be dead is impossible unless something is pushing it. The drillers were confused. Why do we have pressure? Dewey Rivette and the assistant driller, Stephen Curtis, looked at the data. They bled the line again. They tried to get it back to 0. Every time they bled it, the pressure came back. This is the definition of a failed test. The well was talking to them. It was telling them in the only language it has, hydrostatics, that the door was open. The cement had failed. The gas was communicating with the pipe. But this is where the psychology of the schedule from hell intercepted the reality of the science. Enter the company men. Donald Vidrine, the senior BP site leader on duty, came to the drill shack. Vidrine was an experienced man. He had decades in the oil field, but he was also a man under immense pressure to finish. The rig was 43 days behind. Every hour they spent troubleshooting was costing tens of thousands of dollars. When he saw the 400 psi reading, he didn't see a disaster. He saw an anomaly. He saw a glitch. The human brain has a dangerous defect called confirmation bias. When we want a specific outcome, we tend to interpret ambiguous data in a way that supports that outcome. Vidrine wanted the well to be sealed. He wanted to go home, so he looked for an explanation that would allow the test to pass. He, along with the Transocean crew, began to theorize. Maybe it's the bladder effect. This was the phrase that would doom 11 men. The bladder effect was a theory, unproven and scientifically dubious in this context, that the heavy mud in the riser pipe was somehow pushing on the annular preventer, the rubber seal, compressing it like a bladder and causing a false reading on the sensor. It was a phantom explanation for a phantom seal. But it sounded plausible enough to a room full of tired men who wanted to believe it. It can't be the well, the logic went. We just cemented it. The cement job went fine. It has to be the sensor. It has to be the mud. To prove this theory, they decided to run the test again. But this time, they would use a different line. They would test the kill line instead of the drill pipe. The kill line is a smaller high-pressure pipe that runs alongside the main riser. They opened the valve on the kill line. They bled it to 0, and this time the fluid stopped. The pressure held at 0. The men in the shack exhaled. "See," Vidrine argued. "The kill line is 0. The well is dead. The pressure on the drill pipe was just the bladder effect." But this was a fatal misinterpretation of fluid dynamics. The kill line reading was 0 because the valve was likely blocked, or the fluid in that specific thin line was stagnant. The drill pipe, the main artery, was still showing 400 psi. In a safety-critical industry, if you have two sensors and one says safe and the other says danger, you must assume danger. You have to assume the well is live until proven dead. But they didn't do that. They chose the data point that they liked, the kill line, and ignored the data point that scared them, the drill pipe. It was 7:55 p.m. The debate in the drill shack was over. The consensus was reached. The 400 psi was dismissed as a mechanical anomaly. Donald Vidrine gave the order. "The test is good. Open the well." At 8 p.m., the point of no return was crossed. They opened the blowout preventer. This removed the only mechanical barrier between the reservoir and the surface. Then they began the displacement. To finish the abandonment, they had to pump the heavy drilling mud out of the riser pipe and replace it with seawater. This was the trigger. Remember the arm wrestling match? The mud was the only weight holding the gas down. The cement was broken, but the heavy mud column was still providing enough hydrostatic pressure to keep the gas in check. As the pumps fired up and began to push the mud out of the rig and into a supply vessel, the weight on the well began to drop. With every barrel of mud that was removed and replaced with light seawater, the arm of the ocean got weaker. Down at 18,000 feet, the gas seized the opportunity. It pushed through the nitrogen foam cement. It entered the casing. And because gas is lighter than mud, it began to float. As gas rises in a column of liquid, it expands. Boyle's law. If you have a bubble of gas at the bottom of the ocean under 5,000 psi, it is compressed and small, but as it rises, the pressure decreases. The bubble gets bigger. As it gets bigger, it pushes the mud above it faster. This creates a feedback loop. The faster the mud moves out, the less pressure is in the well. The less pressure, the more the gas expands. The more it expands, the faster it moves. It is a runaway train, but up in the drill shack, the screens look normal. This is the tragedy of the test that lied. It gave them a sense of security that was completely false. From 8 p.m. to 9 p.m., the crew went about their business. The roughnecks were cleaning up the floor. The mudloggers were monitoring the returns, but the data was there. If you look at the logs from that night, which investigators later did, you can see the signs. The flow meters showed anomalies. The pump pressure fluctuated, but no one was looking for a kick. Why would they? They had just passed the negative pressure test. In their minds, the well was dead. They weren't looking for a monster because they had convinced themselves the cage was locked. They were looking at the sensors, but they weren't seeing them. The gas was now racing up the riser pipe. It was moving silently through the cold water of the Gulf, shielded by the steel walls of the pipe. It passed the 10,000-foot mark. It passed the 5,000-foot mark. It passed the barp on the sea floor. It was now in the riser, the umbilical cord connecting the seafloor to the rig. The test that lied had done its job. It had convinced the gatekeepers to open the gates. At 9:30 p.m., the gas was just a few thousand feet below the drill floor. It was expanding exponentially now. It was pushing a massive slug of mud ahead of it. The crew was about to experience the mud rain. But as they stood there in the drill shack at 8 p.m., satisfied with their logic, shaking hands on a job well done, they couldn't hear the whisper of the methane. They couldn't feel the vibration building in the steel. They had rationalized their own destruction. They had looked at the red light of danger and, through the sheer force of corporate pressure and wishful thinking, convinced themselves it was green. And in doing so, they had signed the death warrants of 11 men. Chapter 6. The Displacement. At 8:02 p.m. on April the 20th, The Deepwater Horizon was a scene of industrial efficiency. The negative pressure test had been declared a success. The company men were satisfied. The green light had been given. To the 126 souls on board, the danger was over. They believed they had successfully capped the beast. Now, it was just a matter of cleaning up and going home. But in reality, 8:02 p.m. was the moment they stopped holding the door shut and began to actively open it. The next phase of the operation was called displacement. To understand why this phase was the trigger for the catastrophe, we have to look at the fundamental physics of deep-sea drilling. It is a game of balance. It is a constant high-stakes seesaw match between two immense forces. On one side, you have the reservoir pressure. This is the energy of the Earth. At the bottom of the Macondo well, the oil and gas were pushing up with a force of roughly 12,000 pounds per square inch, psi. This force is constant. It never sleeps. It wants to equalize with the surface. On the other side, you have the hydrostatic pressure. This is the weight of the fluid inside the drill pipe pushing down. For the entire drilling process, the crew had kept the seesaw tipped in their favor. They did this by filling the hole with drilling mud. This mud isn't just dirty water. It is a highly engineered chemical soup, thickened with minerals like barite to make it extremely heavy. The mud used on the Deepwater Horizon weighed about 14 pounds per gallon. That is almost twice as heavy as regular water. As long as this heavy mud was sitting in the pipe, its sheer weight acted as a lead lid. It created a downward pressure that was greater than 12,000 psi. It crushed the gas back into the rock. It kept the monster in the cage, but you can't leave a rig attached to a well forever. To disconnect the Deepwater Horizon and move it to the next job, they had to remove the mud. They had to disconnect the riser pipe, the umbilical cord, from the wellhead on the sea floor. You can't dump drilling mud into the ocean. It's a pollutant and it's expensive. You have to pump it back up to the rig and store it in tanks. So, the plan was to push the mud out of the riser pipe and replace it with seawater. Seawater is light. It weighs only 8.6 pounds per gallon. This is where the math becomes lethal. When you replace 14-pound mud with 8.6 pounds seawater, you are drastically reducing the weight pushing down on the well. You are taking the lead weights off the scale, one by one. If the cement seal at the bottom was solid, if the phantom seal was actually real, this wouldn't matter. The cement would block the reservoir, and the weight of the fluid in the pipe would be irrelevant. But as we know, the cement was a sponge. It was compromised by nitrogen channels. The only thing keeping the gas out was the heavy mud. And at 8:02 p.m., the crew turned on the massive pumps to remove that mud. The process involves a spacer. You can't just mix mud and water, they will contaminate each other. So they pump a pill, a slug of heavy viscous fluid, to act as a squeegee, separating the mud from the seawater pushing behind it. As the seawater began to fill the pipe, descending from the rig down to the sea floor, and then pushing the mud back up, the hydrostatic pressure at the bottom of the well began to drop. It was a slow, sliding scale. 8:10 p.m. The pressure is still high enough to hold the gas. 8:20 p.m. The seawater is deeper now. The overall weight of the column is lighter. The pressure is dropping. 8:30 p.m. The tipping point. At a certain specific moment during the displacement, the hydrostatic pressure inside the well dropped below the pressure of the reservoir. The seesaw tipped. Deep in the darkness of the Miocene rock, the methane gas sensed the weakness. The invisible door that had been held shut by the mud was suddenly unlatched. The gas began to move. It pushed through the defects in the nitrogen foam cement. It bubbled through the shoe track, the bottom section of the pipe. It entered the steel casing. This was the influx. At first it wasn't a roar, it was a stealth invasion. Methane, C1, is a hydrocarbon gas. It is clear, it is odorless, and deep down, under high pressure, it can be dissolved in oil-based mud, making it hard to detect. But once it was inside the pipe, the laws of thermodynamics took over. Boyle's law states that the volume of a gas is inversely proportional to the pressure. Simply put, if you decrease the pressure, the gas expands. When a bubble of methane enters the bottom of a well at 5,000 psi, it is compressed. It is small. It looks like nothing. But as it rises, the pressure decreases. The bubble grows. And as it grows, it displaces more mud. This creates a terrifying feedback loop known as unloading the well. Imagine a bubble rising in a soda bottle. As it goes up, it pushes liquid out of the way. In the drill pipe, when the gas pushes mud up and out of the rig, the total weight in the pipe decreases even more. Gas is lighter than mud. So, gas enters. Weight drops. More gas enters. Gas expands. Weight drops faster. Gas shoots up. It is an exponential acceleration. It turns the drill pipe into a cannon. But up in the driller's shack, the crew was blind to what was happening beneath their feet. They were monitoring the flow out. In a closed system, what you pump in should equal what you get out. If you pump in 10 barrels of seawater, you should get 10 barrels of mud out. If you get 11 barrels out, it means something else has entered the pipe. It means you have a kick. During the hour of displacement, there were signs. The data was screaming, but it was screaming in a language the crew had been conditioned to ignore. At 8:50 p.m., the pumps were paused for a sheen test to check if the mud was clean enough to discharge. During this pause, with the pumps off, the well should have been static. There should have been no flow, but the drill pipe pressure gauge slowly rose. The driller, Dewey Rivette, noticed it. He was a veteran. He knew what pressure build-up meant. But again, the shadow of the bladder effect hung over the room. They had just spent 3 hours convincing themselves that pressure readings were glitches. They assumed the pressure was just thermal expansion, the cold seawater heating up in the warm well. They bled the pressure off. They ignored the warning. At 9:00 p.m. they resumed pumping. By now the gas wasn't just trickling. It was rushing. The gas had migrated up past the 5,000-foot depth. It was passing the blowout preventer on the sea floor. It was entering the riser, the 21-inch diameter pipe that connected the seafloor to the rig. Once the gas enters the riser, it is game over. The riser is not designed to hold pressure. It is just a conduit, and importantly, above the seafloor, the pressure drops rapidly. The expansion of the gas went vertical. A bubble that was the size of a beach ball at the bottom of the well was now expanding into the size of a bus. It was pushing the massive column of mud above it with the force of a freight train. The displacement was no longer controlled by the pumps. It was being driven by the geology. On the rig floor, the first physical signs began to appear, but they were subtle. The mud in the return pits, where the fluid comes up, started to rise faster than it should have. The pumps were pushing at a set rate, but the pits were filling up too quickly. The gain-loss alarm in the mud logging shack should have sounded, but the alarm limits had been adjusted or inhibited to prevent false alarms during the displacement activity. The system was muted. The crew was busy converting the rig for transit. They were thinking about helicopters. They were thinking about home. They didn't realize that they were standing on top of a 3-mile-long cannon barrel, and the fuse had already burned down. The seawater, which they had pumped in to save money and time, had done exactly what physics said it would do. It had lightened the load. It had invited the enemy in. The U-tube was unbalanced. The heavy mud was almost gone. The light seawater was in place, and the gas was racing through the void, expanding, accelerating, and preparing to breach the surface. The displacement phase was finished. The well was now fully unloaded. The silence of the deep ocean was about to be broken by the sound of the earth screaming. The kick was here. Chapter 7. The Kick. The ocean is often compared to space. It is vast, hostile, and alien. But there is one crucial difference. In space, if a seal breaks, the pressure rushes out. In the deep ocean, the pressure rushes in. By 9:00 p.m. on April 20th, the Deepwater Horizon had lost its battle with that pressure. The displacement was complete. The heavy mud that had acted as a shield was gone, replaced by light seawater. The hydrostatic balance had tipped. The U-tube was no longer stable. Deep in the well, 18,000 feet down, the gas was no longer trickling. It was surging. A massive bubble of methane, a slug, was racing up the riser pipe. Because of the physics of expansion, this wasn't linear growth. It was exponential. Every foot it rose, the pressure on it decreased, and the bubble grew larger, pushing the column of fluid above it faster and faster. It was silent. The pipe ran through the cold, dark water, hiding the violence within. But on the rig floor, the silence was about to end. At 9:40 p.m., the first clear sign appeared, and it wasn't on a computer screen. It was visceral. The drilling crew was in the process of displacing the riser. They were pumping seawater down to push the remaining mud out. But suddenly, something strange happened. The pumps were running, but the pressure in the drill pipe jumped. Driller Dewey Rivette saw the spike. He was a veteran. He knew that when you pump fluid into a hole, the pressure should be steady. If it spikes, it means something is pushing back. "Shut it down," he ordered. They killed the pumps. In a normal situation, when the pumps stop, the flow should stop. The returns, the fluid coming back up out of the well, should cease immediately, but they didn't. The crew looked at the monitors. The flow meter was still spinning. Fluid was still pouring out of the well and into the mud pits. "The well is flowing," someone yelled. "This is the nightmare scenario. This is a kick." The crew reacted. Instantly. They did exactly what they were trained to do. They moved to shut in the well. The first line of defense is the annular preventer. This is a massive rubber donut inside the blowout preventer, BOP, stack on the sea floor, 5,000 feet below. When activated, it squeezes tight around the drill pipe, sealing the annulus, the space between the pipe and the rock. Dewey Rivette hit the button to close the annula. He waited. On the screen, the pressure readings should have stabilized. If the annula sealed, the kick would be trapped below it. The pressure would rise to a certain point and then hold. But the pressure didn't hold. It kept climbing. It shot up from 1,200 psi to 2,300 psi in a matter of seconds. The annula had failed, or rather, the gas was moving so fast and with such violence that the rubber seal couldn't hold it back. The gas was likely already above the BOP stack when they closed it. The monster was already in the room. At 9:42 p.m. the gas reached the surface, but it didn't come up as a cloud. It came up as a projectile. The slug of gas was pushing a massive column of heavy drilling mud ahead of it. This mud, moving at incredible speed, hit the top of the derrick. Whoosh! A geyser of black, oily mud shot 240 feet into the air. It coated the derrick. It rained down on the drill floor. It smashed onto the deck, slippery and thick. The mud rain. For a split second, the crew was stunned. It was a surreal sight. But then, the training kicked in. Diverter. Diverter. The diverter is a system designed for exactly this moment. It is a set of valves that directs the flow of gas and mud away from the rig floor and out through pipes on the side of the ship, the overboard lines. But the system failed, whether due to a malfunction or the sheer volume of the flow. The gas wasn't diverted overboard. It was routed into the mud gas separator, MGS. The MGS is a piece of safety equipment designed to separate small amounts of gas from the mud. It looks like a large tank. It is not designed for a full-scale blowout. It is designed to handle a garden hose, and the well was feeding it a fire hose. The MGS was overwhelmed instantly. The pressure inside it skyrocketed. The gas blew through the liquid seal at the bottom of the tank. Instead of venting safely, the gas flooded the rig. A white hissing cloud of methane enveloped the drill floor. Methane is heavier than air in its cold state, but as it warms, it rises. It filled the moon pool. It drifted into the engine rooms. It was 9:46 p.m. The driller, Dewey Rivette, and the tool pusher, Jason Anderson, were still on the floor. They were fighting. They knew the annular hadn't worked. They had one card left to play, the variable bore rams, VBRs. Inside the BOP stack, below the annular, are massive steel rams. They are like hydraulic gates. When activated, they slam together with millions of pounds of force, crushing the pipe and sealing the hole. Rivette hit the button for the VBRs. EDR. Close the VBRs. They watched the panel. The lights indicated the rams were moving. but down in the dark, physics was working against them. The flow of gas was now supersonic. The erosion caused by the sand and debris in the mud was stripping away the steel of the pipe. The pipe itself was vibrating violently, whipping back and forth inside the casing. The rams closed, but they didn't seal. The pipe might have been off-center, remember the missing centralizers, or the pressure was simply too high. The gas bypassed the steel gates. The crew was out of options. The rig was now shaking. It wasn't a subtle vibration anymore. It was a roar. The sound of high-pressure gas venting is deafening. It sounds like a jet engine taking off inside a closet. The hissing noise became a scream. At 9:47 p.m., the gas cloud reached the engine intakes. The Deepwater Horizon was powered by massive diesel engines. Diesel engines work by compressing air and fuel until it ignites. They don't need spark plugs. If you feed a diesel engine an atmosphere full of methane gas, it doesn't need its own fuel injectors anymore. It sucks in the gas-rich air and burns it. The engines began to run away. In the engine control room, the RPM gauge is redlined. The engines revved uncontrollably. They screamed higher and higher, spinning faster than they were designed to go. The lights on the rig flared blindingly bright, then surged, then popped. The power grid destabilized. "We're losing power! We're losing power!" Then the overspeed safety trips kicked in. The engines tried to shut down, but a diesel engine running on atmospheric gas can't be shut down by cutting the fuel line. It's eating the air. The only way to stop it is to cut the air intake. But the intake valves didn't close fast enough, or the gas was already inside. One of the engines backfired, or perhaps a spark from the electrical surge hit the cloud. It doesn't matter what. The specific ignition source was. The result was chemistry. Methane plus oxygen plus spark. Inferno. 9:49 p.m. Boom. The first explosion ripped through the engine room. It was massive. It blew out the bulkheads. It shredded the steel walls. But the gas cloud wasn't just in the engine room. It was everywhere. It was on the drill floor. It was in the mud pits. It was hovering over the deck. Seconds later, the second explosion occurred. This was the big one. This was the one that turned night into day. The entire drill floor, the area where Dewey Rivette, Jason Anderson, and 9 other men were working, was instantly consumed by a fireball. The blast wave was supersonic. It smashed through the accommodation block. In the galley, men were thrown across the room. Ceiling tiles collapsed. Doors were blown off their hinges. The city at sea went dark. Then, the fire took hold. The Deepwater Horizon carried over 1 million gallons of diesel fuel for its own use. But the fire wasn't burning diesel. It was burning the earth. The well was now an open volcano. The pipe was a torch. The oil and gas coming up from the reservoir were feeding the fire with infinite fuel. The men who survived the initial blast scrambled in the darkness. Their ears were ringing. The air was filled with smoke and dust. Fire! Fire! Abandoned ship! The alarms finally started to sound, but they were almost drowned out by the roar of the fire. Up on the bridge, the captain, Kurt Kuchta, tried to assess the damage. He looked out the window toward the drill floor. It was gone. There was no drill floor. There was just a tower of flame reaching hundreds of feet into the sky. The derrick, that massive steel tower, was wrapped in fire, groaning as the heat began to soften the steel. The kick was over. The battle for control was lost. The well had not just kicked. It had punched the rig in the face. The shut-in procedures, the annular preventer, the variable bore rams, the diverter, system, every single layer of defense had failed. Some failed because of mechanical issues. Some failed because of maintenance neglect. Some failed because the physics of the blowout were simply too violent. But ultimately, they failed because the initial barrier, the cement, was a ghost. The men on the drill floor never stood a chance. They were standing on top of a shotgun barrel when the trigger was pulled. They fought to the very last second, hitting the buttons, trying to close the gates, trying to save the ship. But the physics of 18,000 feet deep does not negotiate. The kick had transitioned into a blowout, and the blowout had transitioned into a catastrophe. The rig was dead in the water. No power, No thrusters, no control, and the fire was growing. Chapter 8. Ignition. The universe has a way of waiting until the worst possible moment to align the laws of physics against you. On the night of April 20th, 2010, at 9:45 p.m., the Deepwater Horizon was no longer a drilling vessel. It was a loaded weapon, and the safety had just been clicked off. The kick had delivered its payload. The well had vomited a massive invisible cloud of methane gas onto the deck. To understand the horror of what happened next, you have to understand the nature of the gas itself. Methane, CH4, is the simplest hydrocarbon. In its natural state deep underground, it is under such immense pressure that it behaves almost like a liquid. But when it hits the surface atmosphere, it expands violently. It is odorless, it is colorless. You cannot see it until it condenses water vapor from the air, creating a white, ghostly fog. By 9:47 p.m., this fog had swallowed the Deepwater Horizon. It rolled over the drill floor. It poured down into the moon pool. It drifted into the shaker rooms where the mud was processed. It was heavy, cold, and silent. The rig was now swimming in fuel. Usually fuel needs a delivery system, a pipe, a hose, a nozzle, to get to the engine. But when the air itself becomes fuel, the machines that rely on air to breathe become suicide machines. This is the phenomenon known as diesel runaway. The Deepwater Horizon was powered by 6 massive Wärtsilä 18 V32 diesel engines. These were the beating hearts of the city at sea. They generated the 40 megawatts of electricity needed to run the lights, the computers, the drilling equipment, and the massive thrusters that kept the rig stationary. A diesel engine is unique. Unlike a car engine, it does not use spark plugs. It relies on compression. It squeezes air until the air gets so hot that when fuel is injected, it explodes spontaneously, driving the piston down. The speed of the engine is controlled by limiting the amount of fuel injected. If you want to slow down, you cut the fuel. But on this night, the engines were sucking in air that was saturated with methane. In the engine control room, ECR, the alarms began to scream. The RPM gauges on engine number 3 and engine number 6 didn't just climb, they spiked. The governors, the mechanical devices designed to regulate speed, tried to cut the fuel supply. They closed the diesel injectors. In a normal situation, the engines would have shut down. But the engines didn't care about the diesel. They were eating the air. The methane-rich atmosphere provided an unlimited, unregulated fuel source. The engines began to rev uncontrollably. They spun faster and faster, pushing past their red lines. The massive steel pistons hammered up and down with terrifying speed. The screaming whine of the turbines rose to a pitch that vibrated the fillings in the crew's teeth. The electrical grid of the rig surged. The lights in the galley, the cabins, and the bridge flared blindingly bright. Light bulbs popped. Computer screens sizzled and died. The rig was having a seizure. In the ECR, the engineers tried to hit the E-stop, emergency stop. This button is supposed to close a flap on the air intake, choking the engine. But the gas was already inside. Or perhaps the flaps failed to close against the suction of the runaway turbines. The engines were now spinning so fast that they were physically tearing themselves apart. A connecting rod, a piece of solid steel as thick as a man's arm, likely shattered. Then, inevitably, came the spark. It might have been a backfire from the over-revving engine. It might have been an electrical arc from the exploding light bulbs. It might have been static electricity generated by the rushing gas. It doesn't matter what the source was. The chemistry was waiting. 9:49 p.m., the first explosion. It happened in the engine room. A blast of overpressure ripped the heavy steel doors off their hinges. It blew out the bulkheads. It sent a shockwave traveling through the ventilation ducts of the ship. This first blast was the primaire. It woke the rig up. Up on the bridge, Captain Kurt Kuchta felt the ship lurch. The dynamic positioning system failed instantly. The thrusters died. The screens went black. "We have lost power. Fire in the engine room." But the gas cloud wasn't just in the engine room. It was everywhere. It was hovering over the drill floor, where Dewey Rivette and his crew were frantically trying to close the rams. It was filling the derrick. It was settling on the deck. 10 seconds later, the second explosion. If the first explosion was a grenade, the second explosion was a nuclear bomb. The initial blast ignited the massive concentration of gas that had accumulated on the drill floor and in the derrick. The entire center of the ship detonated. The physics of this explosion are difficult to comprehend. It wasn't just a fire, it was a concussion. The blast wave moved at supersonic speed, expanding outward in a perfect sphere of destruction. On the drill floor, the temperature instantly spiked to over 2,000 degrees Fahrenheit. Steel didn't just bend, it melted. The derrick, that 200-foot tower of iron, was turned into a chimney for the sea inferno. The blast wave hit the accommodation block, the hotel where the crew lived, like a sledgehammer. Inside the galley, men were watching a movie. 1 second, they were relaxed. The next second, the ceiling tiles disintegrated. The walls blew in. The air pressure changed so violently that it ruptured eardrums. Men were thrown across the room, slammed into bulkheads, buried under debris. Windows made of reinforced stormproof glass were shattered into dust. But the true tragedy, the heart of the horror, was on the drill floor. There were 11 men working in the immediate vicinity of the well center: Dewey Rivette, Jason Anderson, Stephen Curtis, Donald Clark, and 7 others. They were the roughnecks. They were the ones who had fought the well for the last hour. They were the ones who had stayed at their posts, trying to activate the BOP, trying to close the diverter, trying to save the ship. When the second explosion hit, they were at ground zero. There was no time used to run. There was no time to scream. The blast consumed the entire drill shack and the surrounding deck instantly. We often use the phrase vaporized in movies, but in an industrial hydrocarbon explosion of this magnitude, the reality is starker. The force of the blast would have disintegrated the structural integrity of the room they were standing in. The heat was intense enough to incinerate organic matter in milliseconds. They didn't suffer. Their brains wouldn't have had time to process the nerve signals of pain before the end came. One moment they were working, fighting for their lives. The next moment they were gone. They became part of the fire. The explosion didn't stop at the drill floor. It traveled up. The methane had filled the riser pipe all the way to the top of the derrick. The derrick acted like a cannon barrel. A massive column of fire shot 500 feet into the night sky. From 40 miles away, on the supply ship Damon Bankston, the crew saw the horizon ignite. It looked like the sun rising in the middle of the night, one witness said, but it rose in 2 seconds. The Deepwater Horizon, the billion-dollar city, was now a volcano. The fire wasn't just burning the gas in the air, it was burning the crude oil that was now gushing out of the pipe. Crude oil doesn't burn cleanly. It burns with a thick, choking black smoke. It produces a radiant heat that is physical. It feels like a solid weight pressing against your skin. On the bridge, the blast had shattered every window. The captain and his officers were picking themselves up off the floor, bleeding from glass cuts, stunned by the concussion. The emergency alarms were finally sounding, a high-pitched rhythmic wail that cut through the roar of the flames. Mayday! 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 This is Deepwater Horizon. We are on fire. We are abandoning ship. But the radio was static. The antennas had been melted. The rig was dead. The power was gone. The thrusters were silent. The only light came from the inferno that was consuming the center of the vessel. The survivors, the men and women in the galley, in the cabins, in the gym, began to stumble out into the hallways. The emergency lights flickered on, casting a sickly green glow over the smoke-filled corridors. Confusion reigned. What happened? Did a bomb go off? Where is the drill crew? Nobody knew. All they knew was that the air was getting hot, the floor was tilting, and there was a sound, a continuous, roaring thunder that told them the world had ended. The ignition phase was over. The accident was no longer a well-controlled situation. It was a survival situation. The Deepwater Horizon had become a burning island, and for the 115 survivors stumbling through the dark, the realization was starting to set in. They were 41 miles from land. The water below them was black and covered in oil. The fire above them was hot enough to melt steel, and the only way off was to jump. The 11 men on the drill floor were gone. They were the first casualties of the Macondo War, but the fire they left behind was now hunting the rest of the crew. The physics of the explosion had done its work. Now, the psychology of panic took over. The city at sea was sinking. The unsinkable rig was burning, and the long, terrifying night of the evacuation had just begun. This wasn't just an industrial accident. It was hell on earth, and the door had just been blown off the hinges. Chapter 9. The 11. In the lexicon of disasters, numbers often replace names. We talk about the 5500 on the Titanic. We talk about the 29 on the Edmund Fitzgerald. We talk about the 126 on the Deepwater Horizon. But statistics are a way of distancing ourselves from the truth. The truth is not a number. The truth is a face. The truth is a father, a brother, a husband. When the second explosion ripped through the center of the rig at 9:49 p.m., it didn't just destroy machinery. It erased a brotherhood. At the exact moment of ignition, there were 126 people on board the rig. 115 of them would eventually make it to the lifeboats. They would be burned, battered, and traumatized, but they would go home. 11 men would not. To understand the tragedy of the 11, we have to understand the geography of the drill floor. We have to look at where they were standing and what they were doing in the final seconds of their lives. They were not bystanders. They were the front line, soldiers. They were the ones who saw the mud rain. They were the ones who wrestled with the pressure. They were the ones who stayed at their posts, trying to close the rams, trying to divert the flow, trying to save the rig until the very instant the air turned to fire. These are their names, and this is where they were. The drill shack. The epicenter of the blast was the driller's shack, that glass-enclosed control room overlooking the rig floor. This was the brain of the operation. Inside the shack were the leaders of the drill crew. Dewey Rivette, 48, was the driller. He was a legend in the offshore world. He had been with Transocean for decades. He was the man in the cyber chair, the man with his hands on the joysticks. Dewey was known for his calm, his experience, and his love for his family in Mississippi. In the final minutes, it was Dewey who recognized the kick. It was Dewey who shouted the commands. It was Dewey who hit the button for the variable bore rams. He died. Doing his job, his eyes likely fixed on the pressure gauges, fighting the well to the last breath. Standing next to him was Stephen Curtis, 40, the assistant driller. Stephen was the second set of eyes. He was a man who was respected for his work ethic and his quiet strength. He was there to support Dewey, to verify the data, to help manage the crew. He was a husband and a father of 2 teenagers. Also in or near the shack was Jason Anderson, 35, the tool pusher. The tool pusher is the manager of the rig floor. Jason was a rising star. He was smart, ambitious, and deeply religious. He was a father of 2. He had actually been scheduled to leave the rig the next day. His bags were packed. He was in the shack because that's where a leader stands when things go wrong. He was overseeing the decision to divert the flow. Donald Clark, 49, was the senior assistant driller. He was one of the most beloved men on the crew. They called him Duck. He was known for his humor, his kindness, and his ability to fix anything. He had been preparing to go to bed when the trouble started, but he stayed to help. These 4 men were the brain trust. When the gas cloud ignited, the drill shack was instantly engulfed. The explosion shattered the glass, collapsed the roof, and raised the temperature to thousands of degrees in a fraction of a second. They didn't run. They didn't abandon their post. They were found by the fire while they were trying to save everyone else. The rig floor. Outside the shack, on the metal grating of the drill floor, were the roughnecks and floor hands. These are the men who do the heavy lifting. They handle the pipe. They maintain the equipment. They are the muscle. Shane Rochedeau, 22, was a floor hand. He was young, strong, and full of life. He was from Mississippi. He had written a note to his wife just days before, telling her how much he missed her. He was on the floor, likely cleaning up the mud from the initial spew, when the world ended. Adam, Wisa, 24, was the youngest of the lost. He drove a big pickup truck and loved to hunt. He was a kid living a man's life, working one of the most dangerous jobs on earth to build a future. He had told his friends that this was his last hitch. He wanted to find a safer job. He was standing near the rotary table. Carl Kleppinger Jr., 38, was a floor hand and a veteran of the Gulf War. He was a tough guy with a soft heart for his family. He had spent years working the rigs. He was out on the deck, exposed to the gas cloud when the spark hit, the mud pits and shaker house, below the drill floor, in the complex labyrinth of tanks and pipes where the drilling fluid is processed, were the mud engineers. Gordon Jones, 28, was a mud engineer for MI Swaco. He wasn't a roughneck, he was a specialist. His job was to monitor the chemistry of the drilling fluid. Gordon was expecting his second child. His wife was pregnant. He was in the shaker house, likely trying to understand why the mud was flowing so fast, why the pits were filling up. Keith Blair Manuel, 56, was the senior mud engineer. He was a fanatical LSU fan and a grandfather. He was a mentor to the younger guys. He was alongside Gordon, watching the mud returns, when the gas overwhelmed the mud gas separator and blew through the room. The support Roy Wyatt Kemp, 27, was a derrick hand, but he was often working the pits or the floor. He was a quiet, devoted father who loved the outdoors. He was a man who took pride in the hard, dirty work of the rig. Aaron Dale Burkeen, 37, was the crane operator. His death is particularly heroic. Dale wasn't on the drill floor. He was up in the crane cab, high above the deck. When the explosion started, the rig began to tilt. The massive crane, weighing tons, was swinging dangerously. If it crashed into the deck, it could crush the lifeboats or the survivors. Witnesses say that Dale Burkeen didn't immediately jump. He stayed in the cab. He tried to secure the crane. He tried to move it away from the chaos. The explosion or the subsequent fire consumed the crane tower. He sacrificed his own chance at evacuation to ensure the crane didn't become a weapon against his shipmates. The silence. The horror of Chapter 9 is not just in the explosion itself, but in the immediate aftermath for the survivors. After the blast, there was a moment of stunned silence before the screaming began. The survivors, the men in the galley, the technicians in the pump room, the officers on the bridge, scrambled out into the hallways. They were covered in dust. They were bleeding, but their first instinct was to do a head count. "Where is the drill crew? Has anyone seen Dewey? Has anyone seen Jason?" They called out on the radios. "Drill shack, this is bridge. Report. Static. Floor, this is bridge. Report. Static. Dale, come in. Static." The silence on the radio was the most terrifying sound in the world. It was the sound of a hole in the universe where 11 men used to be. The survivors gathered on the lifeboat deck. They were in shock. They looked toward the center of the rig, hoping to see their friends running out of the smoke. But there was no drill floor. The area where those 11 men had been standing was now a crater of fire. The derrick had turned into a twisted skeleton of melting steel. The heat was so intense that the paint on the lifeboats hundreds of feet away was starting to blister. The realization hit the survivors like a physical blow. They are gone. They didn't just die. They were erased. The violence of a hydrocarbon explosion of this magnitude means there were no bodies to recover. There were no remains to send home. The physics of the blast converted matter into energy instantly. This creates a specific kind of trauma for the survivors. They were leaving the rig, but they were leaving their brothers behind. The muster station logic fell apart. In a drill, everyone goes to their station, you count heads, and you leave. But on April 20th, the count was wrong. "We have 115 souls," the safety officer yelled over the roar of the fire. "We came with 126. The rest are on the floor. There is no floor." The panic was rising. The heat was cooking the skin of the men standing on the deck. The captain had to make the call. They couldn't wait any longer. To wait was to die. They had to lower the lifeboats. They had to leave the 11 behind. As the lifeboats descended toward the black, oil-slicked water, the men looked back up at the inferno. They weren't looking at a machine anymore. They were looking at a pyre. The Deepwater Horizon had been a city, a home, a workplace. Now, it was a tomb. The loss of the 11 is the emotional anchor of this entire story. It changes the narrative from a story about environmental damage or corporate negligence into a story about human cost. These men weren't CEOs. They weren't decision makers in London or Houston. They were the ones with grease under their fingernails. They were the ones who trusted the plan. They were the ones who trusted the cement. They were failed by the engineering. They were failed by the management. They were failed by the negative pressure test. And in the end, they paid the price for the schedule. As the lifeboats hit the water and the motors fired up to pull them away from the burning giant, the names of the dead hung in the smoky air. Anderson, Rivette, Curtis, Clark, Rochedeau, Weiser, Kleppinger, Jones, Manuel, Kemp, Burkeen. They were the first casualties of the Macondo well, but as the fire raged into the night, threatening to sink the entire vessel, the survivors knew that the nightmare was far from over. The rig was dying, the ocean was filling with oil, and the families on the shore were waking up to phone calls that would shatter their lives forever. The 11 were gone. The long morning of the Gulf had begun. Chapter 10. Abandoned Ship. At 9:50 p.m. on April the 20th, the Deepwater Horizon ceased to be a masterpiece of engineering. It ceased to be a billion-dollar asset. It became a burning cage. The transition from normal operations to survival mode was instantaneous. There was no transition period. There was no warning siren that preceded the blast. One moment, men were drinking coffee, playing cards, or showering. The next moment, the world was upside down. For the 115 survivors, the next 60 minutes would be the longest of their lives. To understand the evacuation, you have to understand the geography of the nightmare. The rig was massive, a floating city. But the fire had consumed the center. The derrick was a torch. The drill floor was a crater. The flames were so intense that they were creating their own weather system, sucking in oxygen and generating wind. The explosion had knocked out the main power. The rig was plunged into darkness, illuminated only by the flickering green glow of the emergency lights and the terrifying pulsating orange glare of the inferno, the bridge, the dead stick. On the bridge, Captain Kurt Kuchta and his officers were reeling. The blast had shattered the windows, filling the command center with glass and debris. The screens that monitored the well, the thrusters, and the GPS were black. The captain tried to regain control. He tried to activate the emergency disconnect system, EDS. The EDS is the nuclear option. It is a button that triggers a sequence of hydraulic shears in the blowout preventer on the seafloor. It is supposed to cut the drill pipe, seal the well, and disconnect the rig from the riser, allowing it to float away from the danger. It is the ultimate fail-safe. Kuchta hit the button. Nothing happened. The connection to the seafloor had been severed. The communication lines were melted or blown apart. The BOP was dead. The rig was tethered to the volcano, unable to move, unable to stop the flow. "We have no control," an officer yelled. "We are dead in the water." Fire alarms were finally screaming, a high-pitched rhythmic wail that competed with the roar of the venting gas. The sound of the gas was deafening, a jet engine pitch that vibrated the bones. Kuchta made the only decision left. Abandon ship, get to the lifeboats. The muster, order in chaos. The crew of the Deepwater Horizon was well trained. They drilled for this every week. When the alarm sounded, their muscle memory took over. Despite the concussion, despite the bleeding ears and the shock, men began to move toward the lifeboat stations. But the rig was changing shape. The explosion had damaged the structural integrity of the vessel. The fire suppression system, the deluge guns, had failed, or the piping was destroyed. The rig began to list. It tilted to one side. Walking down a corridor in the dark is hard. Walking down a smoke-filled corridor that is tilting at a 5-degree angle, covered in debris, while the air temperature rises by the second, is a nightmare. The survivors converged on the lifeboat deck. There were 2 main lifeboat stations. The scene was surreal. These were tough men, roughnecks, roustabouts, engineers. They were used to danger, but the look in their eyes was pure primal fear. They did a head count. They screamed names. Where is the drill crew? Where is Jason? Where is Dewey? The silence from the drill floor was the answer. The lifeboats. The struggle to launch the Deepwater Horizon was equipped with modern enclosed lifeboats. These weren't open rowboats. They were bright orange, fire-resistant capsules designed to drop from the deck into the water. But launching them was not simple. The heat from the fire was radiant. It wasn't just hot air, it was infrared radiation. It felt like standing inside a microwave. The paint on the side of the rig facing the fire was bubbling. The plastic on the lifeboats was hot to the touch. As the men piled into the first lifeboat, the panic threatened to break the discipline. Go! Go! Lower it! But there was a problem. The lifeboat engine wouldn't start, or the lowering mechanism was jammed. The list of the rig made the angle wrong. The boat was scraping against the side of the hull. Finally the motor caught. The boat jerked downward. Inside the capsule, it was pitch black and suffocatingly hot. Men were crammed shoulder to shoulder, praying, crying, vomiting from the smoke inhalation. They hit the water with a splash, but the water was not a sanctuary, the sea of fire. The ocean surface was covered in a mixture of drilling mud, diesel fuel, and the crude oil that was beginning to rain down from the sky. The water was slick and black, and in patches it was burning. The lifeboat pilot gunned the engine. He had to get away from the rig before the fire spread to the water around them, or before the rig collapsed on top of them, but not everyone made it to a lifeboat. The jump. For some of the crew, the path to the lifeboats was blocked by fire or debris. For others, the lifeboats were full or had already launched. They were left with one option. The deck of the Deepwater Horizon was roughly 60 to 70 feet above the water. That is the height of a 6-story building. Jumping from that height is lethal if you land wrong. If you hit the water flat, it's like hitting concrete. You break ribs, you rupture organs, you get knocked unconscious and drown. And they weren't jumping into a swimming pool. They were jumping into the dark, oil-covered Gulf of Mexico at night, surrounded by falling debris. Andrea Fleitas, the dynamic positioning operator, was one of those who found herself trapped. She was on the bridge. The fire was closing in. The heat was unbearable. She looked over the railing. Below her, the water was black, reflecting the orange hell above. "Jump!" someone screamed. She climbed over the rail. She hesitated. The instinct of self-preservation screamed, "Don't do it." But the fire screamed louder. She let go. The fall takes about 2 seconds. In those 2 seconds, you are falling through smoke and sparks. Splash. She hit the water. The impact was brutal. The cold salt water rushed into her nose and mouth. But it wasn't just water, it was oily sludge. She surfaced, gasping for air. Her life jacket kept her afloat. Around her, other men were bobbing in the waves. Over here, swim away, swim away. They had to swim. The rig above them was groaning. The derrick was melting. Huge pieces of steel were breaking off and crashing into the sea. If the rig capsized, the suction would pull them all down. So they swam. They swam through the oil. They swam toward the only hope they had. The Ark, the Damon Bankston. The Damon Bankston was a supply vessel that had been tethered to the Deepwater Horizon, waiting to receive the drilling mud. When the explosion happened, the captain of the Bankston, Alwyn Landry, became the unacknowledged hero of the night. Most captains, seeing a massive explosion, 500 meters away, would pull back to a safe distance. Landry didn't. He disconnected his hose and moved closer. He drove his ship right into the danger zone. He knew there would be men in the water. The crew of the Bankston scrambled to the deck. They threw rescue nets over the side. They launched their fast rescue craft, FRC. Look for lights. Look for strobes. The life jackets of the Horizon crew had strobe lights. In the darkness, they looked like fireflies bobbing in the oil. The Bankston's FRC sped through the water, pulling swimmers out. "I got one. Grab his arm." They hauled Andrea Fleitas out of the water. They hauled the roughnecks who had jumped. They were slippery with oil, shivering from shock, eyes wide with trauma. Meanwhile, the lifeboats from the rig began to approach the Bankston. The transfer was chaotic. Men were limping, burned, blinded by soot. They climbed onto the deck of the supply ship and collapsed. The view from the deck, as the survivors gathered on the deck of the Damon Bankston, huddled under blankets, receiving first aid, they finally had a chance to look back. The sight was apocalyptic. The Deepwater Horizon was unrecognizable. It was a tower of fire. The flame reached hundreds of feet into the air. The smoke blotted out the stars. The heat was so intense that they could feel it on their faces even from half a mile away. The silence returned. The screaming had stopped. The shouting had stopped. There was only the roar of the fire and the lap of the waves. The captain of the Deepwater Horizon, Kurt Kuchta, began the grim task of the roll call. He stood on the deck of the rescue ship with a clipboard. Anderson, silence. Rivette, silence. Curtis, silence. Name after name. 11 times the answer was silence. The survivors looked at each other. They looked at the burning rig. They realized that their friends were not in the water. They were not in the other lifeboat. They were still on the rig. The realization settled over the group like a heavy blanket. The adrenaline faded, replaced by a crushing grief. They watched as the fireboats from the Coast Guard arrived, shooting useless streams of water onto the inferno. It was like trying to put out a volcano with a squirt gun. The Deepwater Horizon was dying, and as the Damon Bankston finally turned its engines toward the shore, carrying the 115 shattered survivors, they left behind the burning tomb of the 11 men who had paid the ultimate price for the schedule from hell. The evacuation was over. The search and rescue was beginning, but deep down, everyone on that boat knew there was no one left to rescue. The city at sea was burning down. Chapter 11. The Sinking. The sun rose on the morning of April 21st, 2010, over a scene that looked less like the Gulf of Mexico and more like a scene from a war movie. The Deepwater Horizon was still there. It was a testament to the sheer structural integrity of the vessel that it hadn't disintegrated immediately. It had absorbed 2 massive explosions. It had been gutted by a supersonic shockwave. It had been burning for 9 hours with a heat intensity that defied measurement, but it was still floating. To the Coast Guard pilots flying overhead, and to the crews of the supply ships circling warily in the distance, the rig looked like a mortally wounded giant. The derrick, once the proud vertical symbol of drilling power, was now a blackened, twisted skeleton, wreathed in thick, choking smoke that trailed for miles across the sky. The fire was not abating. In fact, it was feeding. The Deepwater Horizon carried 700,000 gallons of diesel fuel for its own engines. But that wasn't the primary fuel source anymore. The well was open. The rig was acting as a chimney for the reservoir deep below. The oil and gas were roaring up the riser pipe, hitting the surface, and igniting. It was an unquenchable torch, the battle to save the corpse. The response was immediate and overwhelming. A flotilla of vessels descended on the site. Coast Guard cutters, commercial tugboats, and platform supply vessels, PSVs, surrounded the burning rig. Their mission was twofold: search for the 11 missing men and save the ship. The search and rescue operation was frantic. Helicopters scanned the water in grid patterns. Small boats navigated through the oil slick, looking for any sign of a life jacket or a strobe light. But as the hours dragged on, the hope faded into a grim realization. The only thing in the water was debris. Meanwhile, the firefighting ships began their assault. They unleashed water cannons, monitors, on the rig. Dozens of streams of high-pressure salt water arched through the air, hitting the burning hull. The intention was noble: cool the steel, prevent the heat from melting the pontoons, keep the rig afloat so that investigators could board it, so that the well could be capped, so that the bodies could be recovered. But in a tragic twist of physics, the firefighting effort likely hastened the end. The Deepwater Horizon was a semi-submersible. It relied on a delicate balance of buoyancy. It floated on pontoon legs that were compartmentalized. As the fireboats poured millions of gallons of water onto the deck, that water had nowhere to go. The drainage systems were destroyed or clogged with debris. The water pooled in the hull. It flowed into open hatches. It added thousands of tons of weight to a structure that was already compromised. The rig began to list, the slow death. Throughout the day of April 21st, the list became more pronounced. The rig started to lean dangerously to the starboard side. From the deck of the Damon Bankston, the survivors watched their home dying. It was a slow, agonizing process. The city at sea was losing its fight with gravity. As the rig tilted, the internal contents began to shift. Massive cranes, drilling pipe, machinery and furniture slid across the decks, crashing into bulkheads with the sound of thunder. The noise of the dying ship, the groaning of metal, the hissing of steam, the roar of the fire was apocalyptic. The heat was so intense that the paint on the hull was blistering and peeling off in sheets. The aluminum helipad, where so many crews had landed over the years, melted and dripped like wax into the sea. By the night of April 21st, it was clear that the Deepwater Horizon was doomed. The Coast Guard pulled the fireboats back. It was too dangerous. If the rig capsized, it could create a suction vortex that would pull the smaller vessels down with it, or the massive riser pipe could snap and whip around like a striking snake. They waited. April 22nd, Earth Day. The irony of history is often cruel. The date was April 22nd. It was Earth Day, a global holiday dedicated to environmental protection. At 10:21 a.m., under a bright clear blue sky, the Deepwater Horizon gave up the ghost. The final moments were captured on the video by the surrounding ships. It didn't plummet like a stone. It rolled. The list increased until the deck was vertical. The massive derrick, weakened by the fire, crashed into the sea with a colossal splash. Then, the pontoons lost their buoyancy. With a final gargantuan groan of escaping air and twisting steel, the 33,000-ton vessel slipped beneath the waves. It took only a few minutes for the surface to clear. Where there had been a burning tower just moments before, there was now only a patch of bubbling, churning water. A thick, rainbow-colored sheen of oil began to spread rapidly outward. The Deepwater Horizon began its long descent to the bottom of the Gulf, 5,000 feet down. It would crash into the seafloor roughly 500 feet northwest of the wellhead, landing upside down, a crushed monument to the disaster. The kink. The sinking of the rig was a tragedy, but most people assumed it was the end of the event. The rig is gone, the fire is out, now we clean up the spill. They were wrong. The sinking was not the end. It was the beginning of the spill. Here is the mechanics of the second disaster. The rig was connected to the well by the riser pipe. This was a 5,000-foot-long steel straw, 21 inches wide. When the rig sank, it didn't just attach. It pulled the riser pipe with it. The pipe was made of high-strength steel, but it wasn't designed to support the weight of a sinking city. As the rig fell, it dragged the pipe down, but the pipe was bolted to the blowout preventer, BOP, on the seafloor. Something had to give. The pipe didn't snap clean at the base. Instead, it bent. It buckled. It created a kink, just above the bob, like a garden hose folded in half. Then, the pipe broke further up, closer to the rig. The result was a tangled mess of steel spaghetti on the ocean floor. The realization. For a few hours after the sinking, there was a sense of false hope. The fire was out. The smoke cleared. The Coast Guard and BP officials looked at the water and saw some oil, but they assumed it was just the diesel fuel from the rig's tanks and the oil that had been in the riser. They thought the well had sealed itself. They hoped that when the riser kinked, it had pinched the flow off. The best-case scenario, they told the press, is that the weight of the sinking rig crimped the pipe shut. But down in the dark, the ROVs, remotely operated vehicles, were descending. These robotic submarines, equipped with lights and cameras, were sent to inspect the wreckage. What they saw on their monitors chilled the blood of every engineer in the control room. They found the end of the broken riser pipe lying on the sandy bottom. It wasn't crimped. It wasn't sealed. It was spewing. A jet of black fluid, a mixture of crude oil and natural gas, was blasting out of the jagged end of the pipe like a fire hose. It was turbulent. It was violent. It was dark grey against the black water. They moved the ROV to check the BOP stack. They found leaks there too. The kink had not stopped the flow. It had only restricted it slightly. The reservoir, with its 12,000 psi of pressure, was pushing the oil past the obstruction. The math was terrifying. Initial estimates from BP and the government were low. They said 1,000 barrels a day. Then 5,000 barrels a day. But the video footage didn't lie. The flow was massive. Later analysis would show it was closer to 60,000 barrels a day. That is 2.5 million gallons, every single day. The sinking of the rig had removed the only thing that was burning the oil off, the fire. Now, the oil wasn't burning. It was entering the water column. It was dissolving. It was spreading. It was rising to the surface to form a slick that would eventually cover 68,000 square miles. The tomb, the sinking, changed the nature of the Deepwater Horizon site forever. It was no longer an industrial accident site. It was a grave. The bodies of the 11 men, Dewey Rivette, Jason Anderson, and the others, were never recovered from the rig before it went down. The fire had been too hot, the structure too unstable. When the rig sank, it took them with it. They are still there, 5,000 feet down, encased in the steel of the machine they died trying to save. The Deepwater Horizon wreckage is now a protected site. It is a somber, silent place in the crushing darkness. But on April 22nd, 2010, the focus wasn't on the grave. It was on the nozzle. The world watched as the realization set in. The machine is gone. The men are gone. But the valve is open, and we don't know how to close it. The Macondo well had become a monster that could not be killed. The fire was out, but the bleeding had just begun. The ocean was about to turn black. Chapter 12. The Black Tomb. The sinking of the Deepwater Horizon on Earth. Day 2010 was not the end of the story. It was the beginning of the siege. For the next 87 days, the world watched in slow-motion horror as the Macondo well bled into the Gulf of Mexico. It was a hemorrhage that no tourniquet seemed capable of stopping. The event shifted from a frantic rescue mission to a grinding technological war against the Earth itself. The images from the ROV cameras became the wallpaper of the nightly news. That grainy dark video feed showing the plume of black oil and gas billowing out of the broken riser pipe burned itself into the collective consciousness. It looked like smoke pouring from a smokestack, but it was underwater. It was violent, unrelenting, and toxic. The numbers were staggering. Initially, BP estimated the flow at 1,000 barrels a day, then 5,000. But scientists analyzing the video saw the truth. The flow was closer to 60,000 barrels a day. That is 2.5 million gallons of crude oil entering the ocean every 24 hours. The failed solutions. The desperation of the engineers in Houston and London led to a series of attempts to stop the flow that, in hindsight, seem almost primitive. First, they tried the cofferdam. They built a massive 100-ton steel containment dome, a giant box, and lowered it 5,000 feet down to place it over the leak. The idea was to funnel the oil up to a ship, but physics intervened again. Methane hydrates, ice crystals formed by gas and water under pressure, clogged the dome instantly. It floated away, useless. Then they tried the junk shot. This is exactly what it sounds like. They pumped garbage into the blowout preventer. They shredded tires, knotted ropes, and even golf balls, injecting them into the stack at high pressure. The hope was that the debris would clog the throat of the well, choking the flow enough to pump in heavy mud. It failed. The pressure of the reservoir was too great. The well simply spat the junk back out. Then came the top kill. This was the brute force approach. They hooked up massive pumps to the top of the BOP and tried to shove drilling mud down the throat of the well, directly against the flow of the oil. It was a hydraulic arm wrestling match. For 3 days, they pumped 30,000 barrels of heavy mud, but the well was stronger. The mud was blasted back out. The top kill failed. The relief well, the sniper shot. While these desperate, publicly visible attempts were failing, The real solution was being drilled quietly, miles away. The only way to truly kill a blowout of this magnitude is to intercept the well deep underground. You have to drill a new hole, a relief well, and crash it into the original well bore near the bottom. Then, you pump cement in from the side, cutting off the source. This is a feat of engineering precision that borders on the impossible. The original well was a 7-inch pipe buried in rock, 18,000 feet below the surface. The relief well had to start from a different rig, travel through 5,000 feet of water, drill through 13,000 feet of rock, and hit that 7-inch target. It is equivalent to hitting a dinner plate from 3 miles away while blindfolded in a, say, hurricane. They used a technology called active magnetic ranging. They magnetized the steel casing of the blown-out well. The drill bit of the relief well had sensors that could feel that magnetic field. Like a homing missile, it inched closer and closer. On July 15th, 87 days after the explosion, BP finally managed to place a capping stack, a new set of valves, on top of the flowing well. They closed the valves. For the first time in 3 months, the plume stopped. The bleeding ceased. But the well wasn't dead yet. It was just choked. The final death blow came in September. The relief well, Development Driller 3, finally intercepted the Macondo annulus. They pumped in the cement. This time, there was no nitrogen foam. This time, there was no rush. They pumped it until it was solid stone. On September 19, 2010, the Macondo well was officially declared dead. The aftermath. The war was over, but the battlefield was ruined. The total discharge was estimated at 4.9 million barrels, 210 million gallons. It was the largest marine oil spill in history. The oil didn't just disappear. It coated over 1,000 miles of coastline. It soaked the marshes of Louisiana, the beaches of Florida, and the barrier islands of Mississippi. It killed marine life on a scale that is hard to quantify. Hundreds of thousands of seabirds, sea turtles, and dolphins. But there is a hidden scar, one that is less visible than the oil-soaked pelicans. Much of the oil never reached the surface. It formed massive underwater plumes, rivers of dispersed oil moving through the deep ocean. Eventually, this oil settled on the sea floor. Today, there is a dirty bathtub ring on the bottom of the Gulf of Mexico, a layer of toxic residue that settled over the coral and the sediment. It is a dead zone, the human toll. And what of the human cost? The families of the 11 men, Rivette, Anderson, Curtis, Clark, and the others, were left with a grief that was compounded by the lack of finality. Because the bodies were never recovered, there were no funerals with caskets. The Deepwater Horizon itself serves as their headstone. The wreckage of the rig lies on the bottom, upside down, half buried in the mud. It is a crushed, twisted mass of steel. It is dark. It is silent. It is under 5,000 feet of water. In the legal aftermath, the finger-pointing was immense. BP, Transocean, and Halliburton spent years fighting over percentages of blame. The investigations revealed the normalization of deviance that we discussed, the ignored tests, the skipped maintenance, the rush to finish. BP eventually agreed to pay over $20 billion in fines and settlements. It was the largest corporate settlement in US history. But money does not unburn a father. Money does not pull a husband out of the fire. Conclusion: the hubris of the machine. So, what is the lesson of the Deepwater Horizon? It is easy to look at this as a story about corporate greed, and it is. The schedule from hell drove every fatal decision. But on a deeper level, this is a story about the illusion of control. We built a machine the size of a skyscraper. We floated it on the ocean. We used satellites to hold it still. We drilled a hole 3 miles into the crust of the planet to extract the pressurized remains of prehistoric life. We did all of this and assumed that we were the masters of the transaction. We forgot that the Earth is not a passive participant. The Earth is a pressurized, volatile, living system. It has forces that dwarf our engineering. 12,000 psi is not just a number on a gauge. It is the weight of a mountain pushing back. The men on the Deepwater Horizon were not killed by bad luck. They were killed because the system they worked for believed that the laws of economics could override the laws of physics. They believed that if you ignore the red flags long enough, they will turn green. But nature doesn't negotiate. Nature doesn't care about your stock price. Nature doesn't care about your timeline. When you punch a hole in the tiger's cage, you better be sure the lock is strong. And on April 20th, 2010, we found out that the lock was made of foam and wishful thinking. The Deepwater Horizon is gone. The oil has settled. The news cameras have moved on. But 41 miles off the coast of Louisiana, in the pitch-black cold of the abyss, the wreckage is still there. It sits in the silence, a monument to the 11 men who never came home, and a warning to the next generation of engineers who think they can tame the deep. Sometimes the deep bites back. That is the story of the Deepwater Horizon. It is a difficult story to tell, and a difficult one to listen to. It requires us to look at the intersection of human brilliance and human folly. We are building a library of these stories here, from the ice of the Arctic to the darkness of the caves. If you made it this far, you are part of that community. I want to thank you for respecting the memory of the men we lost by listening to their story in full. If you found value in this deep dive, please check that you are subscribed. We have more stories coming. Stories of the Chernobyl exclusion zone, the submarines lost in the Cold War, and the mountaineers who never came down. You can turn the lights back on now. I'll see you in the dark next time.